Glad to be here with everyone. I've noticed everyone is so creative here. I guess obviously Lauren, but right, even Daniel with Red 6 building your own airplane cannot happen without having an immense amount of creativity. So I find that amazing. Looking forward to Chris's talk. So I'm here to talk about how to make better AR experiences on the hardware side. So I'm going to focus very specifically on waveguides. This is the technology that Lauren was just speaking to in the Snap spectacles. Obviously some interesting news from that company recently. But I'm going to focus more on what Applied Materials is doing to enable this technology. It's a really big company, so I'll just start by giving an overview of what we do and then what my group, Engineered Optics, is building on the optics side of things. So Applied is a public company. You can find its stock. We primarily have business making equipment for semiconductor tools. Semiconductor is a huge topic right now, right? It's at a major inflection point in terms of the size of transistors going down and down to, now even 3 nanometers. And there's a big need for supporting that industry. It's almost kind of like the oil to our current economy right now, with, a lot better environmental implications, I guess I would say. And so it's a big company. We have about 22,000 employees. We're doing many patents and support a lot of R&D spending in the United States. So getting into the group that I work within, Applied Materials has a semiconductor group, display group, global services. So they work with fabs to make sure they can keep running and producing chips. And then there's a CTO group where we work on more innovative ideas. We incubate them and then eventually turn them into businesses. And so Engineered Optics is the biggest group within CTO at Applied Materials. And what we're really doing is taking the expertise that we already have for making this equipment and making nanostructured electronic devices like your transistors I mentioned. And these at the fundamental level are made for manipulating electrons really precisely. And so we're taking that similar concept and building devices that can manipulate photons. So combining all of these things, we can do a couple of different unique applications or solve a couple of different high value problems. I'm going to focus primarily on waveguides for AR glasses. That's kind of my main focus and background and what I love, but there's also a lot of other interesting things that we can do with this platform, one of them being flat optics for near infrared devices. So you can imagine taking a regular thick kind of phone camera module or Face ID module and thinning it down to being very flat, so you don't have that notch on the back of your phone, which is kind of a goal of some companies. And so drilling into the waveguides a little bit. We talked about this, Lauren kind of described it as additive light. And so this gets into a little bit more about how AR waveguide combiners work in a very simple sense. So this is kind of showing light going in here on the display side and then going out to the eye. We're just kind of showing a periscope just for fun. And so you have a display panel or some sort of light modulator that injects light into what's called your input section of your grating. And then kind of like a fiber optic, the light is bouncing or transmitting using total internal reflection through the substrate, whatever material that is. And then it reaches the section where your eye box is. And the goal is to have a display quality that's, as close as possible to what we would expect, like high resolution, very immersive, very uniform. And kind of the bottom line is right now, I think we're in a new incubation stage for the industry, and not a lot of the displays are that great. And so we're working really hard on that, and I'll kind of get into the nerdy details as much as you guys will allow on how we're doing that. So like I said, we're hoping to get towards the state of the art. This is a classic one from the Carl Guttag blog, which if you're an AR hardware fan, then you probably have been here. You can put some test patterns through an AR headset, and typically they come out looking something like this. So this is the state-of-the-art AR display from Microsoft HoloLens. And you can see that there's color uniformity issues. You get kind of lines spreading. It's really hard to read text on a white background. White background is generally like one of the hardest tests that you can throw at an AR headset. And so we need to improve. All right. So just a list of some of the attributes that we're working on improving so you can get to a lot better performance right here. And so we're working on things like the patterning technology. You may have heard of companies that do this using very short wavelengths of light in order to get down to tiny nanostructures. So we're bringing that into play. Duty cycle is kind of, you can imagine, like how you tune the efficiency of a grating when it's spitting light back out to your eye. And then high index, this is what defines the field of view that everyone will inevitably want to ask about with these devices. Oh, what's the field of view? As long as you have a really high refractive index, then you can get to much more immersive displays. That's kind of really the goal. And then other things that are unique to us are, for example, double-sided processing. So if you can have a grating on both sides of the glass, then you've just kind of doubled the throughput of your waveguide plate. And so that's important. I'll get into slanted etch a little bit. This is kind of the secret sauce, what makes us very unique and what I think is going to help us win the market. And then variable etch depth, that's kind of another trick of it that helps you get to better uniformity. And then coatings help finish the devices, and 300 millimeter, right? In semiconductor fabs, all of the devices are made on 300 millimeter substrates. And that's kind of where you need to be at with our waveguides in order to get the best cost for, which is eventually going to come down into what the users pay for this. And so we can do all these things. Getting into kind of the complexity of making a waveguide. I said we would nerd out a little bit together here today. So this is a simplified process flow. This is very different from how folks are making waveguides that you may be familiar with right now. This is not a nano imprint waveguide process flow. This is something much closer to a semiconductor approach. You can see from my virtual background, this is the clean room that we have in Santa Clara. A lot of the tools that we operate are totally under vacuum, and this is required for the best possible particle control and then dimensional performance. And so this is a very simplified flow. First, we're depositing films, so things that are very high refractive index, like I spoke to. Doing patterning, FS means front side, BS means backside, and you can see that we have an etch step in the middle there, and then we go on to characterization. And so we're building all of these capabilities in-house in order to support waveguide manufacturing. Our goal is to bring the best possible devices into the market. All right, so I have another couple of kind of nerd out slides that I hope you guys will enjoy. Back to the high index inorganic materials. So what we've done here is just a simple vapor deposition of a very high refractive index material. You can see they're uniform in their coatings. They're not very rough, and then you can get to very high refractive index. So we're balancing kind of absorption, which is like the clarity that you can see when you're looking through a pair of eyeglasses, with refractive index, which is kind of like your bandwidth for making a very good AR display. And so we offer multiple of these different types of films. So you can build a lot of interesting device architectures with our portfolio of materials. All right. So then getting into image resolution, here we're showing, actually, I think this is a slide from one of the Microsoft guy, Alex Kittman's talks, showing how the manufacturing tolerances are actually immensely important for getting to a good MTF. This is basically the kind of fidelity of contrast as you're passing an image through a waveguide display. And so you can see, basically we're showing that pitch uniformity, or how far off you are from the design target your pitch is, kind of the repeating structure of your gratings, is going to make a huge impact. And so we don't think it's enough to kind of take the cheapest possible manufacturing approach. We think in order to get the best possible display, you need to start by understanding what the levers are and kind of the tolerances in order to get to a good device. And then we also make not just the manufacturing tools, but the metrology is very important. If you can't measure it, then you don't know how much you're off by. And so this is showing just I think a standard piece of glass, what the pitch uniformity is on that, and then the orientation is also kind of like the rotational measurement of how your gratings are set up. All right, so this is kind of the one that gets me very excited, slanted etch. With nano imprint, it's very hard to do this. You generally, with a nano imprint, you need to lay down kind of a resin or a resist layer and then put a stamp into it. Rather than doing that, we're actually kind of subtracting material by using an etch tool that we've made, totally custom development, and that gives you a lot more design freedom in order to make really great waveguides. And so this is showing how we can vary kind of the trench width, as you see here, and that's kind of an impact on the efficiency. And you can just kind of choose where you want that grading width to be on your waveguide. And so this, of course, can be scaled up to high volume manufacturing tool. And then just bringing it all together, kind of the different capabilities that are driving our ability to make some of the best waveguides, right? For productivity, it's 300 millimeter substrates, then the efficiency of the display. So this is kind of something that I don't think we got into with Lauren's talk, but the kind of the battery life of those snap spectacles is very short. It's like under half an hour. And so we need to increase the efficiency, the optical efficiency of these devices. And waveguides are inherently lossy. They throw away a ton of light. And so even a couple of percentage points actually makes a big difference. The metasurface, we think those will come into play on kind of the sensing elements of AR headsets. Uniformity, so we can do local area processing, etch where you want to, that kind of thing. And then I spoke to double-sided processing, so you have those two channels of light for every piece of glass that you're using. And then backend is actually very underrated. It's kind of how you complete the build of a waveguide. It's not enough to just make it on a wafer. You have to cut it up. You have to edge blacken it. You have to characterize it, put it in a frame, and then get a light engine to talk to it. And so we're doing all this with, insane precision and with very high quality materials. Yeah, so we have a broad suite of solutions. We're not wedded to just one process flow. We can do nil as well. We can do etch. We can do single, double, triple sheet, front-sided, back-sided, many different types of processing flows go through our line today. And so we think with our materials and our equipment expertise and metrology expertise, we have kind of a best-in-class platform. So please don't hesitate to reach out. I know this was probably a lot of technical detail in a short time, but I'd love to answer some questions.